Welcome to science class. Today we are going to focus on the life and eventual death of stars, the mass of the sun, and lower. You will commonly hear that the sun is an average-sized star. That's really not true at all. The sun happens to be in the middle with regards to the range that stars come in, but if you were to graph stars by mass, you don't get a normal distribution where the average is in the middle. Instead, it skews way towards the much smaller red dwarf stars. The sun is in the 90th percentile in terms of mass, meaning it is more massive than 90% of the stars we see. This video focuses on stars at and below the mass of the sun. Stars are masses of hydrogen which undergo nuclear fusion in their cores, but that process can't go on forever. Stars have a sort of life cycle, and depending on their mass, the final stages of their life can be pretty dramatic. Let's get started. Let's review the basics of stars. Stars are massive collections of plasma held together by their own gravity. Stars form as the hydrogen within nebulae contracts. Eventually, that hydrogen compresses so much that virtually all of it is converted to plasma, where the electrons are not bound to any one nucleus. The atomic nuclei in the core of the star undergo nuclear fusion, where nuclei combine, creating new elements. Hydrogen fuses into helium, for example. That is the source for virtually all of the heat, light, and other forms of radiation that come from the star. The core only makes up about 20% of the volume of a star, but because that's where all the action happens, it's the part we will focus most of our attention on. The largest stars have the strongest gravity, the most compression, the highest core temperatures, and are the biggest and brightest. The less starting mass, the less extreme the core becomes, and the dimmer and cooler the star. Let's bring up the Hertzsprung-Russell diagram again. This diagram shows how temperature and brightness are directly correlated, and mass is the reason why. This curvy trend line that runs diagonally through the middle of the diagram is where you find what are called the main sequence stars. The main sequence stage of a star's life is the phase where hydrogen fusion occurs in its core. When the star exhausts all of the hydrogen nuclei in its core, then fusion will either happen outside the core or stop altogether. In any case, no matter how big or small the star is, they all spend about 90% of their lifetime in the main sequence stage. We will discuss what happens after the main sequence stage in this video and the next one. That should be all we need to jump right in. You've probably heard that the brightest star burns out the quickest. This is also true for almost all celebrities, professional athletes, and lottery winners. The rate at which fusion occurs in a star's core depends on pressure. Low-mass stars burn their fuel at a much slower rate than extremely massive stars, whose insane core pressure forces fusion to occur exponentially faster. Blue supergiant stars only last around a few 100 million years or less. Yeah, I know, only a few 100 million years. But red dwarf stars, around a third the mass of the sun, can stay in the main sequence stage for 1 trillion years. 1 trillion years! That's 10,000 times longer than a blue supergiant. But the incredibly long lives of red dwarf stars is aided by another characteristic. In all other stars, the hydrogen nuclei in the core are the only nuclei available for fusion. Outside of the core of stars, like the sun, is what's called a radiative region. Within this region of the star's interior, matter cannot convect. Normally, differences in temperature and density allow materials to convect. But for physics reasons that I don't understand, this cannot happen in stars similar to the mass of the sun or greater. This means that the cores of those stars cannot be refueled by the vast quantities of hydrogen nuclei that sit outside the core. But red dwarf stars are what we call entirely convective. Not only do they undergo fusion at a much slower rate in their core, but all of the hydrogen nuclei within the star circulates and refuels the core. The universe is only about 14 billion years old. Yeah, I know, only 14 billion years old. But these red dwarf stars can last 1 trillion years. We don't really know exactly what they do after they run out of hydrogen nuclei to fuse, because none of them have yet. But we do know that they are not massive enough to fuse helium nuclei into any other elements. It is thought that towards the end of their life cycle, red dwarfs might turn into blue dwarfs as a result of increased surface temperatures. But in any case, red dwarfs eventually become a plasma ball made almost entirely of helium nuclei and electrons, and they will slowly cool over more trillions of years until they no longer emit any heat or light, a black dwarf. Stars with masses between 0.3 to 1.5 times the mass of the Sun have a much different life cycle. Of course, there will be some differences between the high and low ends of these stars, but for simplicity's sake, we will use the Sun as the standard model for what I'm going to call medium mass stars. The Sun will last around 12 billion years. Like all stars, the Sun will spend 90% of that time in the main sequence stage, fusing hydrogen nuclei into helium nuclei in its core. But medium mass stars can generate a few elements heavier than helium, and medium mass stars evolve complexly into a few different possible objects towards the end of their life, rather than the slow and steady cooling of red dwarfs. As helium builds up in the star's core, the core becomes even more dense and hot, but the helium nuclei within it cannot fuse yet. The Sun, in fact, becomes hotter over time, not cooler. What happens next is the hydrogen nuclei just outside the core begin to fuse into helium nuclei. This causes the star to change physically in a big way. Remember that stars are defined as plasma held together by gravity, which pushes inward against the energy released during fusion. That's what defines the physical size of a star, its volume, its diameter. But now, fusion, the force that pushes against gravity, is concentrated outside of the core, and the core makes up a full 1/4 of the diameter of the star. This causes the star to expand dramatically. At first, the change is relatively subtle. The star expands to about twice its original diameter. This causes the star to also change color. Because the star is growing in volume, that means the heat it produces is spread out. Thus, the star changes its surface color to red as its surface temperature drops. In the core, however, things continue heating up. The core does not expand. Only the layers outside of the core and the new fusion region outside the core. As more millions of years go by, the star's outer layers continue to expand. The Sun's outer layers will eventually extend all the way to where Earth is. This is an enormous change. The Sun will have a diameter of 300 million kilometers at this point. Its current diameter is only 1.4 million kilometers. Yeah, I know, only. While this will cause the surface temperatures of the Sun to cool even more, because the Sun is so gigantic, it will be 2,000 times brighter in terms of absolute magnitude. It has become a red giant. Red giants can be found in the upper right-hand corner of the Hertzsprung-Russell diagram. Stars in the neighborhood of our Sun evolve into these stars, so their position on the HR diagram changes. At this point, the outer layers of the Sun are so far away from the core, where gravity pulls mass towards, that these outer layers actually escape. Gravity cannot hold on to them. As much as 1/3 of the total mass of the star ejects away in all directions, forming what is called a planetary nebula. The name is awful because there's nothing planetary about these nebulae. When they were first observed in the 1700s, they appeared round like planets, so the name stuck. Now that we have the Hubble telescope and others, we can see the true structure of these planetary nebulae. They are some of the most beautiful things in the universe. Planetary nebulae can be a light year across, and the intense radiation from the remaining star causes them to glow. Now, while all of this has been going on, the core of the star has not been expanding, it's been contracting and getting even hotter. For physics reasons that I, once again, do not understand, the remaining outer layers of the star no longer release energy, but absorb it instead. This means they cannot push against the force of gravity, so the remaining mass of the star is compressed even further. This allows helium fusion to occur, which creates carbon nuclei and small amounts of oxygen and neon. As this occurs, the star enters a variable stage, where its total diameter fluctuates, which to an observer far away would make the star's brightness fluctuate over time. These are what the Cepheid variable stars I brought up in the last video are. Half of the remaining mass of the star is shed once again and expands in all directions. At this point, the star is dead. Stars with the mass we are discussing cannot fuse carbon nuclei into anything else. The remaining core of the star, composed almost entirely of carbon, now cools for billions of years. This remaining object is known as a white dwarf. At this point, the size of the star is dramatically reduced. The white dwarf is about the size of Earth, but is nothing like Earth. For one, white dwarfs range from 1.2 to 0.15 solar masses. So yes, it is the size of Earth, but upwards of 350,000 times the mass of Earth. The density of these objects is unimaginable. A cubic centimeter of white dwarf material would have a mass of 1 ton, and they are white because they are white hot, up to 35,000 Kelvin, the temperature of blue stars. But because they are so small, they are very dim. The closest white dwarf star to Earth is only 8.4 light years away from Earth, but you need a telescope to see it. Another reason you can't see it with the naked eye is this star, Sirius B, is a binary star with Sirius A, the brightest star you can see at night. One final thing to mention. If a white dwarf happens to be a binary star, and the white dwarf is sufficiently massive, the white dwarf can suck up matter from the companion star, drawing it inward and triggering a special type of supernova, a Type 1a supernova. These types of white dwarf stars must have a mass around 1.4 times that of the Sun in order to trigger these types of supernova. Type 1a supernovae are used as what we call standard candles, which are objects in space of known luminosity used to measure distances. Within the Milky Way, Cepheid variable stars work as good standard candles, but they're less reliable for judging distances to other galaxies. Look at this image. This circle could be a small circle that is very close, or a gigantic circle very far away. Because there are no points of reference within this picture, it's impossible to tell. We have this same problem with galaxies. Space is so empty that it's impossible to tell exactly how far away a galaxy is just by looking at it. We can refer back to what we know about luminosity and absolute magnitude. Type 1a supernova can only occur in certain stars with a certain mass. Therefore, the absolute magnitude of these types of supernovae falls within a narrow range. That absolute magnitude diminishes with distance, which remember is what apparent magnitude is, the brightness of an object we perceive from Earth. When we observe a Type 1a supernova in another galaxy, we can measure its apparent magnitude and calculate how far away the supernova would have to be in order to diminish in magnitude that much. You can think of it this way. We know exactly how much light a 60-watt light bulb puts out, so we can therefore determine how bright the bulb would appear at various distances. It's the same principle, just scaled up quite a bit. That concludes this video on low and medium mass stars. Next time, we are going to discuss the fate of high mass stars. This will include discussing pulsars, magnetars, neutron stars, quasars, other supernovae, and black holes. Hope you're excited. Thanks for watching.